Imagine trying to teach a model to predict what billions of people want to watch, buy, or read next every single day. The scale is staggering. The largest internet platforms see users generating hundreds of billions of interactions daily, and the catalog of possible items refreshes constantly as creators upload new content. For about a decade, the dominant approach has been what's called a deep learning recommendation model, or DLRM. These systems are essentially giant feature engineering machines. Engineers handcraft thousands of numerical signals like click-through rates and ratios, combine them with categorical embeddings for things like user IDs and item IDs, and feed all of this through neural networks designed to find feature interactions. They work, but they hit a wall. As you throw more compute at them, they stop getting better. This is the puzzle the authors set out to solve, and their answer is to throw out most of the recipe and rebuild recommendation systems in the image of large language models. The motivation comes from a striking observation. Transformers scale beautifully with compute in language and vision, following what's called a power law where bigger models trained on more data predictably get better. DLRMs do not. The authors argue this is because DLRMs treat recommendation as a tabular prediction problem with handcrafted features rather than as a sequential modeling problem over raw user behavior. Prior attempts to apply sequential models to recommendation, like treating a user's history as a sequence of item IDs and running a transformer over it, worked in small academic settings but never displaced industrial DLRMs. The reason is that they ignored the heterogeneous features, the billion-scale vocabularies that change every minute, and the sheer computational cost of running attention over sequences that can stretch to 100,000 tokens per user. The author's first move is conceptual. They reformulate ranking and retrieval as what they call sequential transduction tasks, mapping an input sequence of tokens to an output sequence. To make this work, they unify all the messy, heterogeneous features into a single, time-ordered sequence. The main thread of the sequence is the items the user has interacted with. Slow-changing features like demographics or followed creators get compressed and merged in, since they only change occasionally. And here is the bold claim. The handcrafted numerical features like decayed click-through rates can be dropped entirely because a sufficiently powerful sequential model with target-aware attention should be able to learn equivalent representations from the raw categorical sequence. Think of it like replacing a kitchen full of specialized appliances with one very capable chef who learns to do everything from scratch. For ranking specifically, they interleave items and the user's actions on those items, so the sequence alternates between content shown and how the user responded, which lets the model predict the next action given a candidate item. This reformulation unlocks something important on the training side. Traditional DLRMs are trained on impressions, where each user item interaction becomes its own training example with all features recomputed. In the new generative formulation, you train on a user's entire sequence at once and amortize the encoder cost across all the predictions in that sequence. The authors show this drops training complexity by a factor proportional to sequence length, which is how they can suddenly afford to train models orders of magnitude larger. Now for the architecture itself, which they call the Hierarchical Sequential Transduction Unit, or HSTU. At first glance, it looks like a transformer variant with stacked layers connected by residual connections. But several design choices are deliberately different from a standard transformer. First, instead of softmax attention, HSTU uses what they call pointwise aggregated attention. The intuition is that softmax forces attention weights to sum to 1 across the entire sequence, which throws away an important signal. How many prior items in the user's history are actually relevant to the candidate? If a user has interacted with 50 cooking videos, that count itself is meaningful for predicting engagement intensity, not just the relative ranking. Softmax normalizes that intensity away. Pointwise attention preserves it. The authors also argue softmax is poorly suited to non-stationary vocabularies where new items appear constantly. Second, HSTU collapses what would be multiple separate stages in a DLRM, namely feature extraction, feature interaction, and representation, transformation, into a single repeated block. The block computes 4 projections of the input in one fused operation, runs the attention, and then does an element-wise gated combination that serves a similar role to the gating used in mixture of experts models. This dramatically reduces the number of linear layers compared to a transformer, cutting activation memory enough to let them train models more than twice as deep on the same hardware. 2 more clever ideas are worth understanding. The first is stochastic length, which exploits the fact that user behavior tends to repeat at multiple timescales. If you've watched 100 cooking videos, sampling 20 of them probably captures most of the signal. So during training, they randomly subsample long user histories down to much shorter ones with a probability schedule that preserves the longest sequences when they really matter. At their best settings, this removes more than 80% of tokens while barely affecting model quality. The second is mFalcon, an inference algorithm for ranking. When you need to score thousands of candidate items for a single user, you don't want to recompute the user's encoded history for each candidate. mFalcon processes a micro batch of candidates in parallel against a single shared user encoding, modifying the attention masks so each candidate only attends to the user history plus itself. This is conceptually similar to key-value caching in language model inference, but adapted for the recommendation pattern of scoring many candidates against one context. The results are substantial. On academic benchmarks like MovieLens and Amazon Reviews, HSTU beats the best transformer baselines by anywhere from 8 to 66% on metrics like NDCG. On industrial workloads, the encoder is between 5 and 15 times faster than a FlashAttention2 Transformer at sequence length 8192. In live A/B tests on a platform with billions of users, the Generative Recommender improved the main engagement metric by 12.4%, which in the world of mature recommendation systems is an enormous lift. They deployed a model with 1.5 trillion parameters and 285 times the computational complexity of the production DLRM, while actually achieving higher queries per second thanks to mFalcon. Most importantly, they demonstrate that model quality follows a power law in training compute across 3 orders of magnitude, mirroring the scaling laws seen in language models. The DLRM baseline, in contrast, flattens out around 200 billion parameters. Of course, there are caveats. The scaling law claim, while compelling, is established within a single training framework and platform, and we don't yet know if it holds across very different recommendation domains. The decision to drop handcrafted numerical features rests on the assumption that the sequential model can recover them, which the ablations support, but which may not hold uniformly across tasks. The paper also doesn't deeply address cold start users with very short histories, where the generative approach has less to work with than feature-rich DLRMs. And the engineering complexity is real. Row-wise optimizer states placed on DLRM, custom ragified attention kernels, micro-batched inference. All of this requires significant infrastructure investment that smaller organizations may struggle to replicate. Looking forward, the most provocative implication is that recommendation may finally have its foundation model moment. If user actions truly are a modality that scales like language, then a single large generative recommender could potentially serve search, ads, and recommendation across a platform. Learning shared representations of user intent. The paper's title captures it well. actions speak louder than words, and treating them as a first-class generative modality may be the unlock the field has been waiting for. Now let's walk through some questions you might have after hearing all of this. Why does removing softmax from attention actually help, given that softmax has been the default for years? The key insight is that softmax normalizes attention weights to sum to 1 across the sequence, which means the model loses information about the absolute number of relevant prior interactions. In recommendation, knowing that a user has engaged with 50 similar items versus 5 is itself a critical signal for predicting engagement intensity, like how long they'll watch a video. Point-wise, attention keeps that magnitude information intact, which matters when you're predicting calibrated probabilities rather than just relative rankings. How can they justify throwing away all the handcrafted numerical features that DLRMs spent years engineering? The argument is that those numerical features, things like a user's click-through rate on a topic, are themselves derived by aggregating over the same categorical sequence that the generative model now sees directly. If the model has access to the raw sequence and a powerful enough architecture with target-aware attention, it can, in principle, learn whatever aggregation is most useful for the task. The ablation where they fed only the simplified feature set to a DLRM and saw it degrade significantly suggests the HSTU architecture really is doing this work, not just benefiting from the same features. Why does sequence length matter so much more here than in language modeling? In language, a few thousand tokens typically captures a coherent document or conversation. In recommendation, a user's history can stretch back years and contain 100,000 interactions, and the long tail of that history carries real signal about stable preferences. The paper finds that scaling sequence length is just as important as scaling parameters or depth, which is different from the language model scaling laws, where sequence length is often a fixed hyperparameter. This is why they invested so heavily in making attention efficient on very long, sparse sequences. For anyone building large-scale recommendation systems, this paper is a roadmap with very direct implications. The single biggest takeaway is that the feature engineering pipeline you've been maintaining for a decade may be holding back your ability to scale. Consolidating heterogeneous features into a unified sequence representation lets you train end-to-end on raw signals and benefit from compute scaling in a way that DLRMs simply can't. The generative training trick, where you amortize encoder cost across all predictions in a user sequence by emitting one training example per session rather than per impression, is something any team running a streaming training pipeline can adopt and should immediately consider because it directly translates to either much cheaper training or much more data at the same cost. For serving, mFalcon is the kind of idea that pays for itself quickly in a ranking stack. Most production ranking systems already pay the cost of encoding the user once and scoring many candidates, but doing this with full target-aware cross-attention at industrial scale has historically been prohibitive. Micro-batching candidates with shared attention masks combined with key-value caching across requests for the same user makes it feasible to deploy dramatically more expressive models within an existing latency budget. And finally, the demonstration of a scaling law for recommendation should change how teams plan their roadmaps. If quality is predictable in compute, then the investment calculus shifts toward building the infrastructure to spend more compute productively, rather than squeezing diminishing returns out of feature engineering.